let's continue what we left over from last time. We introduced an operator called projection operator. Based on the name as what we discussed, just imagine it's a vector, right? In a 3D space, you have a vector and you say you want to project to something. It's just basically saying that you shine a light to it and try to project to another vector, right? So what I'm trying to say is just an illustration. For example, you have a 3D space and then you have a vector here. And then I say, okay, I want to project to, let's say, the x-axis. This is x hat, right? And this is the projection, right? You project to it and see how much component it has. Make sense? Project, right? I just want to see how much component it has. So, and it is given here, we say that the projection operator, we say we want to project to something, then of course the operator must be described by what you try to project to, right? So for example, we say it's projection operator for vector v. It means we try to project to vector v. So it is the outer product of vector v. Okay? So if I try to apply it to a vector alpha, this is an arbitrary vector, I don't know what it is. I just want to know how much component of v alpha has, right? So what do? We just apply the projection operator, v outer product v, right? This is cat, this is bra, so this is the operator. Apply it to alpha. And then when you do this again, you can use the associative rule, but always be careful how to use the associative rule. You sometimes just think about matrix. So this is a column vector, right? If you really want to do that, I would say, okay, this is a column vector. This is a row vector, right? This is a column vector. And I'm not using associative actually, because these two give you a scalar, right? So it's an inner product. So it's just an inner product times a column vector. So I can put this inner product in front of it. So that's what I'm doing, right? And then I get this. And then you see, it makes a lot of sense, because now I say that I apply the projection operator to alpha. It gives me a vector which is along v. Isn't that the meaning of projection? I want to project to that vector, right? So now I become just that v. But how much? What is the length? It depends on the inner product of v and alpha. And we know that inner product basically try to say how much they overlap, right? Particularly in a 3D real space. Make sense? Right? So just an operation, and it shows that it makes sense. Another example was, okay, what if I have this alpha equal to AB? Then what is the dimension of this vector? What's the dimension of alpha? 2, right? Because I describe it by 2 numbers. And it's equal to A0 plus B1, right? I did not say that, but I tell you that, yeah, we are working on the computational basis. So the first one is 0, the second one is 1, right? Basis state, right? So I try to say, okay, how about I want to see how much 0 component it has. So if the projection operator makes sense, then you should give me A0, because there is amount of 0 component it has, right? So I try to show you. First, projection operator to 0 must be the outer product of 0. Then apply it to alpha, right? Then I try to use matrix form. So you can see that this is, because 0 is, this one maybe I jump a little bit. This is just 0 cat, outer product 0. This is what I'm doing, right? Am I correct? Is that clear? Yeah? Because this is 1, 0, 1, 0. And apply to AB, this is alpha. Then I just do matrix multiplication. 1 times 1 give me 1, 1 times 0 give me 0, 0 times 1 give me 0, 0 times 0 give me 0. So that is the projection operator to 0. Apply to AB, then 1 times A plus 0 times B give me A, 0 times A plus 0 times B give me 0. So this is another vector, A0. I can take out A, right? Because A times 1 equal A, A times 0 equals 0. And 1, 0 is just 0. So this does give me A0. Any questions?
So the projection is actually the measurement, the quantum factor.
The projection matrix.
Yeah, and the action of projection.
Yeah.
Is a measurement.
It's related to measurement. It's not the measurement. I will show you it's related to measure. Related to, we cannot say it's exactly measured, but let's take a look later. But it's related to measurement. You are right. Okay, so I will talk about that later. Now, I just want to emphasize, let's do an exercise, right? This is useful. You will see this, something like this in midterm or whatever. I will call this method 1. It's nothing special. I just use matrix, right? I can use another method to do this calculation. Maybe I call this is just matrix method, right? And now I use bracket. Right, so let's practice. The whole purpose is just to practice. So P0 applied to alpha equals to 0 cat 0 bra applied to alpha. Is this okay? Just right. So what is alpha? Let me continue. This is 0, 0 cat, but alpha is A0 plus B1. Right? That is the alpha, A0 plus B1. And then I'm going to do distribution law, right? I still keep the cat here, and then apply A into it, then I get, 0 into it, I get A, 0, 0, 0 plus B, 0, 1. Is this okay? Because I just apply 0 to here and then 0 to here, just distribution law. Right? You should know this very well. If not, step back, just think about, oh, this is just a row vector. This is column vector plus column vector. I can do row times the first column plus row times the second column. And that is exactly what we're doing earlier. Okay? What is 0 inner product with 0? 1. What is 0 inner product with 1? 0. Because we assume it's orthonormal. Right? So if that is the case, then I get 0A, which is equal to A0. Right? So you get the same thing. So later, when you start working on quantum algorithm, you should be very familiar with this. Okay, and be very careful when you can use associative law, when you can use distribution law. And if you get confused, it's very easy. Just remind yourself which one is number, which one is vector, which one is matrix. And then you use the matrix form to think about that. Okay, so that's projection operator, and he's right. This is related to measurement, and we'll talk about that later. Okay, so how do we use projection operator for measurement? Okay, so this is what we want to say for a state alpha equals to, now I make it general, alpha 0, 0 plus alpha 1, 1 plus all the way to alpha n minus 1, n minus 1. What is the dimension of this state? N, thank you. It has n basis state from 0 to n minus 1, right? Again, 0 to n minus 1 are just some names, right? So I perform a measurement. I do a measurement. Okay, like what he just said. So what is the probability of phi of getting J, state J, right? So what is the probability I will get the basis state J? We say that for measurement, this is a superposition state. Now you know what is superposition. Superposition of many basis states. I do a measurement, what will happen? We said at the very beginning of the class. Collapse. Yeah, good. You gave the right answer, collapse, right? But what is the probability for it collapse to J? And he say alpha J square, magnitude square, right? But yes, so we know that already. We know, and that's what he just said. Just put it red. We know the probability of getting J equals to alpha J square. Now, alpha J can be a complex number. So this is also equal to alpha J times alpha J star. If you forgot, go back to check it. Or if cannot check it, let me know. Any complex number, its magnitude square is equal to itself times its complex conjugate. Is this okay? Okay, so if you forgot, you try to check yourself, okay? Ask ChatGPT, it will prove it to you. Okay, now we know this is the result, right? But more formally, the probability that you will get collapse to J equals to alpha state times the projection operator to J, sandwich it. Okay, so do you see that? Now, every time you see something like that, and if you are not familiar with it, try to analyze again what you are seeing here. What is alpha here? It's a cat. So it's a vector, a column vector. What is PJ? PJ. Matrix. So a matrix times a column vector give you what? Another column vector. So this is a vector. How about alpha bra? Very good. Row vector. Yeah, row vector. Then row vector times a column vector give you what? Scalar. Just like an inner product, right? So this is just a number. Right? It looks confusing, but you know it already. Now, we can also just check carefully, see if this is the case. Alpha Pj on alpha. Again, what is Pj? What is the definition? I mean, the equation. What I'm asking is this. What is Pj? Thank you, the outer product. So it's going to be, I deliberately write it so you can see it. I try. This is equal to J, outer product J. Right, this is bracket, alpha. Right, very confusing, I know, but if you understand, you should know this is bracket, you should not get confused, right? So this is equal to alpha J, J alpha, right? But do you remember the rule? What is the relationship between alpha J and J alpha? Thank you. They are complex conjugate of each other. This one we studied before. I go back to when we talk about bracket property, okay? They are complex numbers, right? So what we're getting here is alpha J. Let me use J alpha instead. That might be better. Although they are the same. This is J alpha star. J alpha, right? And what did we just say? When the when the complex number times its complex conjugate, it gives you the magnitude of that complex number square, right? If you remember what we said on Tuesday, how do you find alpha J? You just recall. So you need to start memorize them, right? Recall alpha J equals to J applied to alpha. What I'm trying to say is your alpha is a linear combination of so many basis states, right? I want to find alpha j. I just do an inner product of j to the whole alpha. Then I will get alpha j. That's what we proved last time. Right? So basically, this one gives me alpha j squared. Right? So a lot of math, but they are not difficult. But you really need to understand them. Make sure every step has a reason. And if you're familiar with this operation, then you can deal with more complicated algorithm. The message is that indeed, the probability of collapsing to the basis state J is just that you sandwich the states, or this is what we call expectation value. We did not really talk about that. It's the expectation value of the projection operator on alpha J, on alpha. Okay, the mean value if you do the measurement. Okay, so many things. First thing, I want you to go back to really understand every step. Be familiar with the tooth. Second, remember that this is how you find the probability for it to collapse. And third, of course, recall these important equations. Okay, any questions? So if no, then we come to a conclusion. What is the relationship between matrix and measurement? You basically don't need to memorize this if you just want to pass the exam, right? Because we're not going to teach you. But this is very important thing that you that help you to understand the meaning of quantum mechanics. There are many different interpretations on quantum mechanics, particularly for its measurement. And one of them is the Copenhagen interpretation or the Born rule. So what does it say? If an observable, firstly, observable is what? It's something you can measure, okay? So for example, maybe we are talking about spin in the z direction. In z, in vertical c. Okay, this is observable, right? We assume the physicists know how to measure the spin of a particle along a certain direction. They can shine a laser and put in magnetic field and then shine a microwave light or laser lights to see whether it emits a photon or absorbs a photon. Then they know whether it's spin up or spin down. We assume we know that. So this is observable, right? It's not by your eye, but we can measure. Observable means something you can measure classically, right? So for example, spin in z-axis. Now, this will have a corresponding operator, okay? So it always has a corresponding operator for the observable. And you need to find it out. It turns out that it is sigma z. What is sigma z again? Do you remember? Pauli matrix, very good. And then one say that he even give the form 1001. Yeah, very good. So Pauli matrix. -1, thank you. You guys did study, huh? Good. Right? So these two looks like not related, but this one corresponds to this. Okay? It will be clearer later. You see why it corresponds to this. But anyway, we say we have an observable classically. And it will correspond to a matrix. And this matrix needs to be self-adjoint or Hermitian. And now you know what is self-adjoint and Hermitian, right? It means that A equals to A dagger. Why? This observable, we only talk about discrete spectrum, okay? It has eigenvalues. It has its eigenvalue, this observable. What are the eigenvalues of this observable? Of this matrix, sorry. 1 and -1, right? Because if you remember, when you represent its in its eigenbasis, then you have diagonal as its eigenvalue, right? And this one we already chose its eigenvector as the basis, 0 and 1 computational basis, right? But anyway, so what does it say again? The observable will correspond to a matrix, and this matrix has some eigenvalue. And when you do the measurement, whatever you get, right, is measured in a system. First, what you get is one of the eigenvalue of A. Okay, the reason you get plus minus 1 is because this matrix has eigenvalue of plus minus 1. That's the first thing. Okay, so no matter how complicated the system is, when you do a certain measurement or how complicated the measurement is, it will correspond to a matrix, Hermitian matrix. And that Hermitian matrix may say, let's say, have 1,000 eigenvalues, for example. Then the only possible value you can get from measurement are those 1,000 possible values. Okay, this is the first thing. And the probability of getting a certain state, the state that is correspond to that eigenvalue, is given by this expectation of this projection operator that we just discussed. Now, it basically you did not learn anything new, but this gives you a more formal description of the meaning of measurement, right? So you can move forward and compare this to other type of interpretation, right? Which we won't cover. But in Nielsen and Chang, they have more discussion. So that's why I say even you don't know doesn't matter, because you already know that the coefficient square is the probability. But turn out this is a more formal approach. But more importantly, something that not everyone is aware of is that observable will corresponds to a Hermitian matrix. And the eigenvalues of the Hermitian matrix are the possible measurement outcome. Okay, so for example, I want to measure the position of the particle. So a particle in quantum mechanics can be in any place. So it is a superposition of every state. So it can be at this point, 0.1 from it, 0.2 from it, and of course it's continuous. This is not discrete. It can be 0.0000123400234 meters from the origin, right? So it is a superposition from negative infinity to positive infinity. So what is the Hermitian matrix corresponding to measuring the position of a particle? You can imagine it would be an infinite matrix because it has infinite number of eigenvalues. Right? But that is a continuous variable thing, right? So getting more complicated. But quantum computing is easy because we usually deal with discrete, right? Only 2D for 1 qubit. Okay, so when we reach here, the goal is to challenge you to have a deeper understanding of what you have learned so far, although they might not be necessary. Okay, so let's do one more thing. Let's practice the projection operator as an exercise. Okay, so assume I have a state which is psi equals to 1 over square root 3, 0, minus I over square root 3, 1, plus 1 over square root 3, 2. First of all, what is the dimension of this 3? Very good. 3 dimension, right? 3D, but not a real 3D because I can have complex number. So this is not a qubit, okay? Not 2 qubit, not 1 qubit. But it can be a quantum state that you have 3 level. We call it Q-tree, I think, yeah. So 3 states, right? So the question, is it normalized? First of all, you always want to ask yourself. He said yes. Okay, then we trust you. Yes, check yourself. Should I do it for you? And please do it. If you cannot get it, email me. Okay, you just make sure the magnitude square sum to 1. Okay, so now my question is a little bit more complicated. What is the probability of measuring 1 or 2? Okay, so now it becomes just like dice problem. What's the probability I will get 3 and 4 when I throw a dice? Right? So I'm going to use of course, we just use a simple method, right? Assume we have not learned the projection operator. What is the probability of getting 1 or 2? Huh?
Loss of the probability.
Thank you. Plus of the 2 probability is like the probability of 1, of getting 1, plus the probability of getting, let me use PORB, otherwise you will think it's a projection operator. The probability of getting 1 plus the probability of getting 2. So what is the probability of getting 1? 1/3, very good. But I want to be clear so that some of you who did not pay attention to yet is the coefficient magnitude square, right? That's why she got 1/3. And then the second one, the probability is 1 over square root 2 squared, right? So it's 2 divided by 3. Okay, so when I do a measurement, I can get state 1 or get state 2. And the probability is 66.66% of the time I will get 1 or 2 when I do the measurement, right? Now, method 2 is just want to demonstrate how to use the projection operator again. The probability is going to be psi projection operator to 1, psi plus psi projection operator to 2. So the reason I'm doing this is just purely to practice the bracket notation, okay? So let's play with this. What is psi bra? Can someone tell me? I'm using bracket notation, so not like column or matrix, right? So what is psi bra? It's 1 over square root 3 bra 0, right? And then minus, someone say plus y. Because you need to do complex conjugate, right? When you do the bra version, the coefficient, if you forgot, C A becomes C star A. Okay, so don't forget this. So this is plus I divided by square root 3, 1 bra, plus 1 over square root 3, 2. This is pretty long, and this is the bra of psi, right? And then what is the projection operator of 1? It's just the outer product of 1. Yeah. Mm-hmm.
The coefficient of that number, so it cannot be equal to the probability, so why do we have to? I understand the coefficient is the magnitude squared, but now I'm confused between the two squared. Between just multiplying psi by a projection of 0 or projection of 1 versus going psi projection of 0 and then psi again.
It's because he's trying to say, isn't that we apply the projection operator, we get the coefficient, but actually you get the coefficient times the vector. You see, is that what you're asking, right? You don't get A, you get A0 cat. So it's a vector. Yeah, but we want to find the probability. That's why. So you have the right point, right? So then you directly will get it. Yeah. So that's the reason. Okay. Then let's continue. Then I will just copy the rest, right? 1 over square root 3, 0, plus minus I square root 3, 1, plus 1 over square root 2. Square root 3, 2. Now you can do the distribution law yourself one by one. But you may say, I already know the answer. 1 to 0 must be 0. 1 to 1 is 1. 1 to 2 is 0, right? Because they are orthogonal. And then this 1 to 2 is 0. 1 to 1 is 1. And then 1 to 0 is 0. Or unlike what he just pointed out, I already know that projection operator applied to this guy will give me the coefficient times the 1, right? So there are many things you can do. I just spelled this out. You don't need to go through this step if you are familiar with that already. Okay? So similarly, for the next step, right? For the next one, I will just directly go to, I'm talking about this 2. I directly know that this must be just I over square root 3, 1, not 1, right? Because we're talking about 2. 1 over square root 3, 2, and then I have this 2 for projection operator, and then the other is 1 over square root 3, 2. So I try to jump the step. Instead of writing this down, I already know that only the 2 term will leave, will be kept, right? So I just put 2 here, and same for the bra. Okay? So the rest, just do the math. Of course, you will get 2 over 3 overall. Right? So the reason I do this, again, I just want to encourage you at the early stages, play with this a little bit more to appreciate this distribution law of orthogonality. And now you will see that it's so beautiful for direct notation. It's not just a notation. By looking at this, you right immediately can get to this form very quickly. Okay? Any questions? This one? This one? Yes. This is the Brown form of psi, right? So you need to take the complex conjugate. That's why you get plus. Yeah, good. Okay. So this is some summary you can try. Okay. Now we go to a